So today I want us to look at the central limit theorem. Now the central limit theorem is a theorem around the distribution of the means. So I'm actually going to start with an example of the distribution of the mean that you should be familiar with. In straight maths, we looked at how if we took a sample from a normal distribution and calculated the mean for that sample, what the distribution of the potential or possible means would look like. And that was referred to as the x-bar distribution, where the mean was mu, the same as the mean from the original normal distribution, but the standard deviation was sigma over root n, or the variance was sigma squared over n. So the variability changed depending on the size of n. Well, that was actually a special case of the central limit theorem. The wider generalized version of the central limit theorem actually says that any distribution with a sufficiently large enough sample size, so a sufficiently large enough value of n, will have its potential mean values, will have its potential x-bar values approximately follow a normal distribution. So it doesn't matter what the original distribution was, the means, the x-bar values, will approximately follow a normal distribution. So you may have taken it for granted before that starting with a normal distribution, its means follow the normal distribution. But now, no matter what type of distribution you have, whether it's positively or negatively skewed, whether it's uniform, bimodal, whether it's symmetrical, whether it has outliers, no matter what distribution you started with, the means are going to follow a normal distribution, where the mean is mu and the standard deviation is sigma over root n, and the variance is sigma squared over n. So that's the central limit theorem. As long as n is sufficiently large, we will get a good approximation for the x-bar distribution, for the distribution of the means. When we mention large enough, we generally mean bigger than 20 to 25. So take that as a rule of thumb. And if you're asked to comment on the reliability of your estimate, this is what we'll refer to, the size of n. The larger it is, the more confident we are in it as an estimate. If n was small, especially if it was smaller than 20, then we would have less confidence in the approximation being close to what the true value may have been. Since we're aware of quite a few specific standard distributions, you will be expected to apply the central limit theorem to all of the distributions you've encountered so far. So you should be able to apply it to the Poisson distribution, to the binomial distribution, to the geometric distribution, and to the negative binomial distribution. For each of these, as long as you can calculate mu and sigma, you should be able to go ahead and find the approximate distribution of the sample means, the approximate distribution of x-bar. So here we're told that a sample of size 9 is taken from a distribution which is a normal distribution where mu is 10 and sigma is 2. Well, can we find the probability that its mean will be greater than 11? Okay, so always stating the original distribution, we're going to then compute the x-bar distribution. Sigma over root n, you know, we like to use that for the standard deviation, and we always give it in the form of standard deviation squared. Well, I can cancel that down quite easily. Root 9 is 3, so this is the distribution we're working with. Let's just get a quick diagram in here. I know that the mean is 10, and I'm looking for greater than or equal to 11. Gives me an idea of what size value I should be getting. It should definitely be smaller than 50%. So just into our calculators from here, the probability of the x-bar is greater than 11. The syntax for the CG50 is to put the minimum value, then the maximum value, standard deviation, and then the mean. So I'm just going to use all of those for this particular distribution. The maximum value, remember, is just an arbitrary, extremely large value since the normal distribution is infinite. Okay, and that gives us an answer of 0.0668 to 4 decimal places. A couple of things to note here. This is not an approximation, since the central limit theorem, when it's applied to a normal distribution, produces the exact distribution of the sample mean. the exact distribution of x bar. So this case, it is not an approximation. Only when the original distribution is not a normal distribution is it an approximation. And with that, once again, the size of n indicates the strength or the confidence we should have in the approximation. The larger the value of n, the more confident we are in the approximation. In this question, n equaled 9, which would be quite a small value, and I would maybe be concerned about applying the central limit theorem. But our original distribution once again was normal, so the sample size didn't particularly matter since we were producing the exact distribution for x bar. Let's go ahead with one more where we're not starting with a normal distribution. So here we've been told about a dice that has its faces changed. We have 3 number 1s, 2 number 3s, and 1 number 6 on the faces of this dice. So we're told that there were 40 trials. The dice was going to be rolled 40 times. So let's just clarify what the random variable is. It's not about the number of successes, it's actually just about the score you get when you roll the dice once. Okay, just to clear that up, some students will look at n equals 40 and start thinking of the binomial distribution, but reading this is about the score you got by rolling the dice just once. Okay, let's actually just write out the distribution, the probability distribution for the score you get when you roll the dice once. 3 possible scores, 1, 3 and 6. Probability of getting a 1, 3 over 6, 3 is 1 over 3, and 6 is 1 over 6. Each of those can be simplified, and let's work with those simplified versions. So a half, a third, and a sixth. Before I can apply the central limit theorem, I do need to calculate mu and sigma. So from this discrete random variable, I know that mu is equivalent to the e of x, the expectation of x, which we calculated by multiplying each of the x values by their corresponding probability and summing them together. In this case, we've got a half plus 1 plus 1. So 2.5 is our expectation. 2.5 or 2.5. We also need to calculate sigma. But in our calculation, we're going to need to make use of the expectation of x squared. So let's just go ahead and do that now. So that's the sum of each of the outcomes, the x values squared, multiplied by the corresponding probabilities. So a very similar calculation. 1 squared multiplied by a half, 3 squared multiplied by a third, and 6 squared multiplied by a sixth. Calculating this, we get 9.5, 9.5 or 9.5 for the expectation of x squared. Okay, from there we're going to move on. Sigma squared is the variance, so I can find the variance of x by doing the expectation of x squared minus the expectation of x squared, and that gives us an answer of 3.25. So the variance, sigma squared, is 3.25, and we know our standard deviation will be the square root of 3.25. Okay, from here we can actually go ahead and form our x bar distribution. So the distribution of the sample means will follow a normal distribution where the mean is mu and the standard deviation is sigma over root n. I do want you to recognize that that is equivalent to saying that the variance is sigma squared over n, and we want to be able to move interchangeably between the two of these, especially since I've calculated sigma squared earlier in the question. I want to make sure I can use both forms of the x bar distribution. Okay, just subbing those values in. So here I've got the variance sigma squared over n, but to get it into our usual form, I'm going to square root and square. Exactly the same value, but it's a better form for putting into our calculators. So now that we've got the distribution, we can go ahead and answer part B, which has asked us to estimate the probability that the mean, so the probability that x bar is greater than 3. So let's not forget diagram. I know the mean value is 2.5, 3 is to the right. We're looking for this shaded region just over here. Well, the probability that x bar is greater than 3, we're really ready to put that into our calculator since we know all the parameters. 3, 10,000 as the arbitrarily large maximum value, putting in the standard deviation here, be careful that this is the form that we wrote, the square rooted version, and the mean of 2.5. Altogether, the probability 0.0397. The central limit theorem. It allows us to find a distribution for the sample mean, or at least an approximate distribution for the sample mean, and the strength of the central limit theorem is that it allows us to have any distribution as our starting point, but we realize that the distribution of the sample means will approximately follow a normal distribution. The size of the sample has an impact on the strength of the approximation, has an impact in our confidence of how well we've approximated any resulting probabilities. As long as you can find mu and sigma for your distribution and the n value is sufficiently large, you will be able to apply the central limit theorem.